Okay, October the 2nd, Monday. What we're going to talk about today is confidence intervals, except what we've done in the past is we've always developed confidence intervals for independent data. If we look at one simulation run, the data produced sequentially throughout the run is almost always correlated. So we need to discuss confidence intervals based on correlated data. In particular, if you want to just do one simulation run and you want to build a confidence interval based on that run, how do you do it? What we've done is, in the past is we've created independent data by simply having separate replicates, and each replicate's independent. Now we're going to look at the building confidence intervals based on just one run with correlated data. Okay. Oops, we're not. Okay. Let's review the what we already have in the past. In the past, we had data that was a random sample. A random sample always means that it was independent, identically distributed. We've had a couple definitions. The excuse me. How do I erase? Okay, let's see. We've had a couple things. Sample mean. X sub n bar. You already have this. I think we have a test scheduled for a week from this coming Friday. The test will include both a lecture portion and a lab portion. The lecture, in other words, material from the lecture and an arena model. So, the test will be closed book, closed notes. Some things you will have to have memorized. This is one of them. Sample mean. I'm going to assume that you know the sample mean. I will assume that you know the sample variance. What's in the denominator here? Why is it n minus 1 instead of n? N seems to be more logical. Why not n instead of n minus 1? Yes, it makes it unbiased. Okay. There is a legitimate estimator for the variance where you divide by the n, and that's called the maximum likelihood estimator. That's biased. So in general, we've been using the unbiased estimator. It's also equal to okay, computationally, the second formula is usually much easier to use. If you're going to be dealing with large data values, then I gave you a one-pass algorithm that would be better to use if you're writing a program. But I do not expect you to have memorized that, so that will not be on the test. Okay, what makes confidence intervals possible, if we talk about a confidence interval for the mean, again, this is based on a random sample, IID data. the expected value of the mean estimator is equal to the overall population, and the variance of this is equal to sigma squared over n, or the estimate for the variance is equal to, okay, again, let me make sure you understand the confidence interval. The idea is that when you estimate you get the sample mean itself is a random variable. Right? So it varies from experiment to experiment. Okay, to build a confidence interval, what we need is the mean of that random variable, namely the mean of the sample mean and the variance of the sample mean. Okay, we have the variance. Of course, that's the variance, but we don't know sigma squared, so we have to estimate the variance. So our confidence interval is really based on the estimate for the variance of the sample mean. Okay, and from there we build a confidence interval. Okay, any questions on that? That's kind of just review what we've already had. Okay, let's now look at slightly different context. We're going to have X sub 1. We're going to have a collection of data. And instead of saying it's a random sample, we're going to say this data is from a covariance stationary process. The word stationary always means that something is independent of time. Stationary always refers to time. Okay, when we say covariant stationary, that means it has the following properties. The mean of each one of these is the same. Notice I have I on the left side but not on the right side. So it says that the mean is independent of time. Okay, if you think of x1, x2, x3 as being a time parameter, then the mean is independent of time. We will also assume that the variance of each one is the same. Oops, no I. Okay, and finally, we're going to say the following, that the correlation the correlation between two of the random variables, and that's going to be defined to be rho of I, is actually, wait. Let me start over. Okay, this is equal to rho sub j. Okay, in other words, we're looking at data. It's independent of I, but not independent of j. Okay, in fact, this is called the lag j correlation coefficient. So again, it's independent of time. It does matter what kind of distance we have between the random variables. In other words, if I'm looking at daily temperatures, okay, Of course, that's not a good example because daily temperatures are not stationary. Because the mean in the summer is different from the mean in the winter, so it's not a stationary process. But we can talk about the lag correlation being, in other words, the correlation between today's temperature and tomorrow's temperature. That would be a lag 1 correlation. Okay? And that's going to be different from the correlation between today's temperature and next month's temperature. That'd be a lag 30 correlation. So you would expect, actually what you'd expect is that the correlation decreases as the lag increases. Okay? So if you have correlated data, you would expect that the correlation between data that are neighbors to each other is going to be much higher than the correlation between data that's far apart. Okay, so if you're looking at, say, waiting times, okay, so I'm getting ready to go in a restaurant, and I ask somebody, well, how long do you have to wait? A long time. Well, chances are, if I just ask the guy, well, I asked the guy in front of me, how long have you been waiting? A long time. Chances are I'm going to have to wait a long time. Okay? But if I go in a restaurant and I ask the guy that came out 3 hours ago, how long did you wait? Not very long. That's not too relevant for me because it's been a long time. So as the lag increases, we'd expect correlation to decrease. Okay, we can no longer use typical confidence interval formulas for this data because the confidence interval formulas is based on the concept of independence. Let me give you some additional formulas. Okay, so we're going to have the sample mean. We'll do exactly the same thing. We still have the sample mean, sample variance. We'll define it the same way. Okay, but now for a covariant stationary process, so we no longer have the independence assumption. Okay. The expected value of x bar of n is still the same. Okay, so that means we can still use the sample mean as the estimator for the overall mean, the true mean. Okay, here's the problem. Let me give you two formulas. Just one. The variance of x bar sub n. That's equal to, right, that's what we had before, but now there's an extra term, times 1 plus 2 times the square root, the sum from j is equal to n minus 1 of 1 minus j over n rho j. Okay, so we have to estimate these lag correlation coefficients to get an estimate for the variability of the mean estimator. Let me give you another formula. If you want to estimate, hats usually mean an estimator. If you want to estimate these formula, it's as follows. Divided by, whoops, and then n minus j of x sub j minus, whoops, messed up again. X sub I minus x bar, x sub I plus j minus x bar, all divided by n minus j. Okay. You do not have to memorize this formula. I will not use it. I give it, there is an estimate. If we wanted to, we could estimate those leg J correlation coefficients. There's problems with it, problems with the estimates. They're biased, they're correlated, and large variance. So if we, in fact, you can see, if you look at, if we wanted to get the n minus 1 leg correlation coefficient, there's only one data point that we can use for that. And so those are terrible estimates. So unless you have a really, really large sample size, and then you got to do a tremendous amount of calculations, this is not a good thing. Technically, we can use that to build a confidence interval. But it's just a highly unreliable thing just because the correlation is so bad. Okay. So, estimating, and I guess there are techniques to do this, but they're just not very reliable. So estimating the confidence interval for a correlated sample set is bad. Okay. What we're going to do instead is we're going to kind of construct the data and into, what should I say, close to independent data. Here's the idea. Let me write, oops. I'm going to demonstrate like, let me write out the data. X1, X2, X3, X4, X5, X6, X7, X8, X9, X10, X11, X12. Okay, we have 12 data points. Okay. Now, most correlated data, again, what happens is that lag J correlation coefficient goes towards 0 if it's large enough. Okay. So what we're going to do is we're going to take this data and divide it up into batches. Let's say we have 12 data sets. I'm going to divide that up into 3 batches as follows. So So I'm going to divide it up into 3 batches. I'm going to group this together and calculate the batch mean for this. So I'm going to have an x1 sub 1. I'm going to call this x2 bar. And I'm going to call this x3 bar. Okay. So now instead of working with those 12 data points, I'm going to work with 3 data points. If my batches are large enough, the assumption is going to be that x1 bar and x2 bar, x3 bar form a almost random sample. That's the idea. Okay? And so then we will build a confidence interval based on those x's. Okay, so let me write this down. Okay, so what I'm talking about is called a batch mean process. 1. Form M batches each of size K. for each batch, form the batch mean, or calculate the batch mean, that'd be a better word. Calculate the batch mean. So then we have X bar 1 through X bar M. Okay? So that each of those batch means is a batch mean formed with K data points. Do you see that? Okay. So now we're going to do our confidence interval based on those batch means. So now we need to calculate X bar bar, which is equal to 1 over M of the summation of I is equal to 1 through M of X sub I, and S I don't know how to denote this, bar squared, which is equal to 1 over M minus 1 of the summation I is equal to 1 through M of X bar sub I squared minus M X bar bar squared. So now our confidence interval is equal to X bar bar plus or minus T with M minus 1 degrees of freedom times S bar divided by the square root of M. Square root of M. I really don't like that S bar. I don't mean by that an average. That's the sample standard. S bar is the sample standard deviation of the batch means. Okay? But conceptually, you just take all the data, divide it up into batches, and then take that as your random sample, and then do a confidence interval as you normally would with that as your random sample. Any questions? No questions. Okay, let's go ahead and pull up Excel. I want to demonstrate a couple things with Excel. Let me save this first. Oh, that's the wrong thing. We want Excel, not Arena. Okay, first I want to demonstrate what happens when we have correlated data. Okay, so I'm going to use, if you still have the homework, there was a homework you did in which I gave the formula for bivariate normal. If you have that, you might get that out. I'm going to use those formulas. It was a couple weeks ago. It was I think the second homework set. It was supposedly due September 13th. That homework, the first problem was about a dispatcher at a fire station. The second problem had to do with the bivariate normal. Okay. So I'm going to use those formulas. Those are great formula for generating correlated data. Okay, so the first thing I want to do in the A1 cell, let's see, first context, what I'm going to do is the following. I'm going to generate data that's normally distributed with a mean 100, standard deviation 25, and I'm going to do it so that the leg 1 correlation is equal to 0.9. Okay, so a fairly high correlation coefficient. Okay, just for demonstration purposes. That's what I want to do. Okay, so the first data point is equal to just the regular random variable that's normal 125. So in the A1 cell, we'll say equals NORMINV, the inverse of the normal, RAND, open close parentheses. The mean is next, that's 100. And then the standard deviation is next, 25. Okay, I need to do a little bit of calculations. Namely, if the correlation is 0.9, I need to calculate what the variance is for the conditional normal. So if you look at that formula, the formula is the following, that the variance of x2 given x1 is equal to any value is equal to the original value, is the original value times 1 minus rho squared. Okay, so that means that's equal to 25 squared times 1 minus 0.9 squared. Okay, so that's 25 squared times 0.19. So that's what we need. Remember that I can't do calculations and have that on the thing at the same time. I need to do an aside. So I'm going to calculate that. I'm just going to use this as a calculator for a minute. So we have the square root of 0.19, I think this ought to work, times 25. So that says, for my correlated data, 10.987. The standard deviation of my correlated data is 10.897. Let me do it one more time. I just want to make sure. 25 times 25 times 0.1 minus 0.9 squared. Good. Okay. Okay. So the next, in the B1, I want to go across because I want to have several random samples. Okay. So the next one is norm inverse. Now this is my correlated random variable. So again I have RAND. The mean, now we have to use the formula because the mean of this is correlated. So the mean depends on the previous random variate. So the mean of the random variate generated in the B1 depends on the value of A1. Okay? And the mean is equal to the original mean, 100, plus rho, which is 0.9 times x is the previous value, so that's times A1 minus 100. Okay? So if A1 is large, the mean, oops, I closed that too quickly. The mean is going to be large. If A1 is small, notice the mean is going to tend to be small. If A1 is right at 100, then the mean is going to be 100. Okay, that's the mean. We also need the standard deviation. The standard deviation is going to be, where did I write that down? 10.897. Okay, I want to have, I'm going to have random sample of size 10. So that's 1, 2, 2, to the right. Okay, that's my random sample. Okay, so that's 10 data points. Now, let's go ahead and form the confidence interval. So at this point, I'm going to, let me label this. I'm going to insert another row so I know what I'm doing. Otherwise, I won't know what I'm doing. In L1, I'm going to put the mean, sample mean. So that's equals average A2 colon AJ. Oops. Oh, okay, yeah, okay, thank you. J2. Okay, here we need the standard deviation. And that's equal to STDEV A2 colon J2. We're going to need the, I'm just going to write this down so it doesn't have to recalculate every time. The T inverse, we're going to have a 5% confidence interval with 9 degrees of freedom. So our T statistic is going to be 2.262157. Okay. Okay, the lower limit is equal to the mean equals L2 minus the T statistic, 2.262157, times the sample standard deviation, which is M2 divided by the square root, square root of 10. Okay, the upper limit is equal to L2 plus the T value, 2.262157, times the sample standard deviation, M2, divided by the square root of 10. Okay. Any questions? Okay, let me highlight that. And wait, how far over does it go? It goes over to P. To P. So I'm going to go down P. So I'm going to. What I want to do is have what we did before. When I was demonstrating confidence intervals before, I think we had 500 different samples. So I want to do the same thing. I'm going to have 500 different samples. So I need to go down to 501. Ah, what happened? Darn. Let me go back up. And do a Control-D to copy down. Oh, you know what else I need to do? I need to say whether it's within it or not. So this is I need an indicator to say whether I have it. If the confidence interval contains the mean, we would expect this is a 95% confidence interval, so we would expect 95% of the confidence intervals to include the true mean. So this is this is indicator. Okay, this is if the logical test. I need two things. I need an AND here, A and D. If work. I need if 100 is greater than 02, comma, and 100 is less than P2. If that's the case, I want to print out 1. Otherwise, I want a 0. Okay. And let me copy that down. And I want to take the average. Equals average of Q2 colon Q501. Does everybody see what I've done? I'm just taking average value of ones and zeros. Supposedly, if it's a good confidence interval, it will be 90. This average should be 95%. 31%. So bad confidence interval. Okay. Actually, what I should have done, I should have let the correlation coefficient be a cell so I can change it easily. But if the correlation coefficient had been 0, this is the same thing we did a couple weeks ago, and it was right around 95%. Okay. So that's the reason when you have correlated data, we have to do something else other than the normal, other than the usual method for getting the confidence interval. Okay. Okay. Any questions? Okay, what I want to do, I want to pass out the homework. It might be good to talk about it before you go off, though. So let me pass it out and let you read it, and then we'll talk about it. Okay. Let me do one other thing here real quickly. Let's say I wanted to, let's say I generated a bunch of data. So this is, let me get rid of this other one. Maybe I should save this. Sorry. Okay. So here we have a bunch of data. If I want to get the correlation of this data, okay, I'd get the correlation. Might as well get more data. Let me go get 100 values. Okay, so here I have a data set of 100 data values. And if I want to get the correlation for it, say the leg 1 correlation coefficient, that's CORREL, I believe. Okay, the correlation has to be between, you have two data sets. If you're trying to get the correlation between an X value and a Y value, we're only off by 1. So what we're going to do is the first data set goes from A1 colon A99. The second data set goes from A2 colon A100. And that's the correlation. Okay, we're leg 1. We're just offset by 1, and those are the two data sets, and that'll give us the leg 1 correlation. Luckily, it's close to 0. Yeah, here if you hit the F9 key, I can't hit my F9 key because it freezes the recording, but if you hit your F9 key, you can see how that value changes. Hopefully, it's always close to 0 because they're just random samples. Okay, so you have a mechanism to get correlation. The first thing I want you to do is use Excel to generate correlated data. And so I just have a mechanism here to get correlated data. I don't even know what the correlation is. I don't remember. I don't know what it is theoretically, but it's obviously correlated. What you'll do is you'll generate in the first element, it's just going to be a regular random number, like RAND. It's the second one that'll make the difference. In the second one, you'll type in this 0.5, then the previous one plus a new random value. You see, so it's correlated because the next cell is always going to depend upon the one right above it. Okay. So what do you think the mean value for this is going to be? What's the mean value of these data? Yeah, it's 0.5. It's going to be a distribution between 0 and 1. But I don't really know what the distribution itself is. It's not uniform anymore. But they're obviously correlated. Now, what I want you to do is, then sequentially, the first 50 points is going to be the first batch. So there's going to be 10 batches altogether. Okay, but before you do the batches, I want you to go ahead and calculate what the confidence interval is. Okay, let me do one other thing. Let's say this is my data, and this is what you're going to have to do. Once you have the data, highlight the data. Okay, highlight the data. Did I put that in the instructions? I didn't do this in the instructions, but you're going to have to do this. Highlight the data, do a copy, okay, and then do a paste special. You might write these down in the instructions. Once you've created your data set, do a copy, then do a paste special, and paste the values only. Okay. There. Now when you look at the data, you've gotten rid of the formula. If you don't do that, every time you do something, you'll change the data on you. So do a copy, then a paste special, and that fixes your data. Okay. Now, once you have your data, pretend like you don't know it's correlated. Okay? And just assume it's somebody gave it to you and they said, here's a random sample. Go ahead and calculate the confidence interval, and that's what goes in this first box. So you'll get one confidence interval and put that down. I just want you to be able to compare the two confidence intervals. So the first confidence interval is wrong because you're going to assume it's not correlated. Okay? And then go ahead and create 10 batches. You're going to have 10 batch means in, because each batch is going to have a mean. Then what you do is you treat those 10 data points as if that were a random sample. And go ahead and fix your confidence interval. You can get an idea of whether it's a good random sample or not by getting the correlation of those 10 data points. I should say you'll get an estimate of the correlation of those 10 data points. Again, with just 10 data points, it's a lousy estimate, but that's as good as you can do, just for comparison. And that will give you an idea whether it's a reasonable estimate or not. Okay, does the homework make sense? Any questions on the homework? Okay, then see if you can do this by Wednesday.